Question number 1. What is the minimum number of poles for a magnet? You know, there are 2 poles, N and S. There are 2 poles, N and S. Each magnet has 2 poles. Even one of the section question was like this. If you break a magnet into 2 pieces, how many poles would each piece have? 2. It doesn't matter how many times you break, because each domain has N pole and S pole. Every magnet has N pole and S pole. And question number 3, an important question. You have 2 iron bars in your possession. 2 iron bars. One of them is magnetized. And you know, iron is a magnetic material. You can keep a magnet close to an iron. Iron becomes magnetized. Domains of the iron is normally randomly arranged. When you keep it close to a magnet, it becomes regularly arranged. And one end becomes N, the other one becomes S pole. And we say that this is a magnet, but not a natural magnet. In physics, sometimes we say induced magnet, this one. When you remove this external magnetic field, after a while, it will turn back to its original state. But we don't know which one is magnetized. There are 2 iron bars. One of them is decided, iron bar A, the other one iron bar B. How can you determine which one is magnetized? Say that one of them is magnetized. I don't know which one, but say A. If iron bar is magnetized, it should have N pole and S pole. Say that this one is N, this is S. Like a compass needle. Compass needle also has N pole and S pole. What does compass needle do when you suspend it in air? Its N pole points to north, geographic pole. S is pointing south, geographic pole. When you suspend it. Same thing. You suspend that. When you suspend these 2 iron bars, the one which is magnetized must align its length in the direction of what? South-north direction. But the other one, how you suspend it, it will stay as it is. It will not rotate. The one which is magnetized will rotate until its length becomes in the direction of south and north. N pole points north, S pole points south. So by this way, by suspending them, by making them able to rotate, we can understand which iron bar is magnetized, which one is not magnetized. Clear? Question number 4. Why does a very strong magnet attract both poles of a weak magnet? It's surprising. Normally N pole attracts S. S pole attracts N. But how S and S attract each other? How N and S, N and N attract each other? This is how it happens. Now, I'm going to show you by the compass example. When I hold N pole of magnet close to a compass, as you see, it faces S. What is happening? N and S face each other. Yani N attracts S. N attracts S. But I can make it opposite. I will do it now. Something I will do a different. Although now what I want to see that. N attracts N. No, what happened? I will explain that. So at the beginning, it was this is what it is. Strong magnet realigns domain of the weak one. Domains, remember, domains are changing directions. When domain direction changes, poles of the compass changes. Now this is not real N pole now. This is S. This becomes N. Yeah, you are changing the direction of the domains. As domain direction changes, N pole of the compass shifts S. S pole of the compass shifts N. When you look at them, you see that red attracts red, white attracts, blue attracts white. But in reality, still they're opposite poles in reality. Yeah. Never N and N attract each other. Never S and S attract each other. But when you do like this, you can make a change in the poles of the compass. Then you can observe that red attracts red, white attracts white. Okay? So what is the basic idea? We are changing the domain directions of this magnet, the weak one, weak one's domain direction changes and poles of the weak one changes. So after that you can observe such a thing, okay? Next question, question number 5. A conductor carrying a current is arranged so that electrons flow in one segment from east to west. So this is the third set, east, west, north, south. So east is to the right of your page, west is to the left of your page, north is top of your page, south is to the bottom of your page. And we are going to put a conductor along east-west direction. If a compass is held over, and above this segment of wire, in what direction needle deflected? In what direction needle deflected means, compass and pole deflects always in the direction of the magnetic field. Then this question is indirectly asking you what is the direction of the magnetic field over the wire. Okay, now I'm going to have a right angle. This is the wire. Its direction is west, east, like this. Electrons are moving from east to west. Electrons are going this way. But electric current and electron motion is opposite. Electric current is going to west to, yes, this is electric current. Electrons are moving in which direction? From east to west, but its current is from west to east. Then I'm going to hold my pen as the electrons, or the conductor. Put the conductor in your palm. So thumb must show where? East. It is east. Then curl your forefinger and keep your fingertips just over the conductor. When you keep it over, your fingernails points this way, which is going to be south. According to the page, because my board is vertical, but page horizontal. This is S, this is north, this is east, this is west. When we hold it like this, so then your fingernails will point which side? It's going to be pointing S of this direction set, okay? So we are going to put the conductor in our palm. Thumb is going to be electric current direction, which is east. Curl your forefinger until it becomes over, stays over the conductor. Then fingernails points which direction? South of your page, okay? So this is the answer of question number 5 in the classroom. In the previous lesson, we did this several times. Next one is about a question about solenoid. What factor does the strength of the magnetic field of solenoid depends on? Yeah, we are going to just think about the equation. What is the equation for solenoid? Mu I n over L. So mu, which is the medium magnetic permeability, I, electric current, N, number of turns, L, length. All of them affects, all 4 effects the magnetic field of a solenoid, but 3 of them are in numerator. Which are they? Mu, I, N. In numerator, they are directly proportional. When mu, I, N, when they are increasing, magnetic field strength increases, but L is in denominator. As L increases, magnetic field strength decreases. Or I can rewrite this equation in alternative form. How? B is equal to mu I times N over L. N over L is known as number of turns per length. So N over L is in numerator, not only L, not L, N over L. So as N over L increases, magnetic field strength of the solenoid proportionally increases too. Okay? Question number 7 is important. It is not asked until now, and maybe it's time for this one. Okay, now let's answer 7. A solenoid with ends marked A and B. So there's a solenoid. My solenoid is in my back. This is a solenoid. I am going to mark one side A, other side B. Okay, this is A, this is B. At least that this red part is B, other side without anything is A and B. We mark them like this. So question says that solenoid with ends marked A and B is suspended by a thread from the ceiling so that it can rotate the core around that. The core can rotate in horizontal plane, not this way. It can rotate like this according to the given question. In horizontal plane, yeah, it will rotate like this. A current is maintained in the coil so that electrons move clockwise. When viewed from A to B, and when you look from A to B, you are going to observe that electrons are going clockwise, this way. Good. So A to B, you are looking, you see electrons are moving clockwise. How will the coil align itself in Earth's magnetic field? We know that if a solenoid or coil or loop, when electric current is given, these circular currents gain poles. One end or one side becomes N pole, other end or other side becomes S pole. Yani it behaves like a compass. Compass also has N pole and S pole. When we suspend the compass needle in air, what happens? N pole points north, S pole points south. Then this is going to be same. When I give electric current to solenoid, one side is going to be N pole, other side is going to be S pole. Then N pole should point north, S pole should point south. Then let's apply. Question says that when we from A to B, you will see that electrons are revolving clockwise. If electrons are clockwise, then electric current must be counterclockwise. So if electric current is counterclockwise, like this, my thumb is pointing which side? A. A is N pole. B is S pole. So N pole points where? North. Where is north? This is north. N pole will point north. Yeah, A will point north. B will point south. This is how it's aligned in itself in a Earth's magnetic field. And don't forget this. Every circular current has poles. Every circular current, loop current, loop, a circular coil, a solenoid, they have N pole and S pole. And if they have N pole and S pole, they can be used as a compass. Yes, they can be used as a compass. N pole of that device points north, S pole points south. Okay, and can you please switch it off? Question number 8. Is it possible to orient a current carrying loop of wire in a uniform magnetic field so that loop will not tend to rotate? We all explained this before. Once again, let's explain. Yes, it is possible. External magnetic field, let me say it is from left to right, like this. When we hold the loop parallel to the magnetic field lines, loop's magnetic field is going to be perpendicular to the external magnetic field. And draw it with another color. This color part. Okay, this is loop's magnetic field. It's going to be like this. So loop's magnetic field is going to be perpendicular to external magnetic field. Remember we said that no two magnetic field wants to cross each other. So one magnetic field should rotate. Of course, which is going to rotate? Loop will start rotating until loop becomes perpendicular to external magnetic field, but loop's magnetic field becomes in the same direction, so no rotation anymore. When loop takes a position perpendicular to external magnetic field, the loop will not tend to rotate. But any orientation different than perpendicular, like this, parallel, it will tend to rotate until it becomes perpendicular to the external magnetic field. Okay, next. If a solenoid were suspended by a string so that it could rotate freely, could it be used as a compass when it's gives direct current? Could it be used if the current were alternating in directions? Okay, if you want to use a device as a compass, it must have a fixed N pole and fixed S pole. Yani poles shouldn't shift. Compass needle has a fixed N pole. One side is N, other side is X. Is it changing? No, normally not, if you don't do anything different. If you want to use a solenoid as a compass, its four poles mustn't be changed. Yani one side must be N, other side should be always S. So if this side always N, electric current must be counterclockwise all the time. Which is direct current is one directional. This direction is not changing. But if direction changes, poles are also changing. N changes to S changes to N changes to S changes. So there is no fixed pole. How can you use this device as a compass in this case? So this is a question. If you want to use not only solenoid, any circular current as a compass, it can be a loop, it can be a circular coil, it can be a solenoid. It must have a fixed N pole and fixed S pole. To have fixed N pole and S pole, electric current must be one directional, yani direct current. Otherwise, alternating current will cause direction to be changed. If direction of the current changes, poles are continuously shifting. Okay? And it cannot use a compass in this case.